The title you already know. The most important way to start, muchas gracias to many colleagues here at the center that I've cooperated with over the years in various fashions. And I will actually be talking about work that is done in collaboration with a colleague here at the Institute, or the Centro. We study an object called the Ring Nebula, and we call ourselves the Fellowship of the Ring. I think the term has been used once or twice before. Here are the members of the fellowship. Gary Ferlin, most famous because of his code Cloudy, which is used by some 1,000 people for research right now. Will Henney, famous for his own good reasons, here at the center. Bob Odell, your speaker. Manuel Pembert at the Instituto de Astronomía, UNAM in Mexico City. And we're studying, well, here you want a picture of the people. It's here. Each person got to pick their model out of the movie characters. But why this strange title for the talk? Recall that story. It originated in India, but it's common to many cultures. The people with a specialty, a way of looking at something, each examine an elephant and come to different conclusions about what is an elephant. And the end result is something that is not really an elephant. And that's the problem with specialists addressing problems. So the team that is this fellowship all have special skills that they apply to the problem. We have studied the Ring Nebula because it's the Goldilocks planetary nebula. It is not too young. It is not too old. That is, it's just the right surface brightness to be studied well, and it does not have too much obscuration, so you can study it thoroughly, and it's an orientation that you can hope to study it in 3 dimensions with some accuracy. So it's the Goldilocks planetary nebula. And there's a fundamental problem in the study of gaseous nebulae that's been around since nearly 40 years since Manuel Pembert first formulated it, the T-squared problem. That is, and it comes down to this, that if you determine abundances of gaseous nebulae from the intrinsically bright, collisionally excited forbidden lines, and compare those abundances with those derived from recombination lines, you get quite different answers. This is an important problem. It's caused by temperature fluctuations, but it's important because when people look at nebulae in other galaxies, and that's the way the abundances in the universe are determined, they use only the intrinsically bright, collisionally excited forbidden lines. So we still don't know the cause of these temperature fluctuations in gaseous nebula. And the goal of this program was to determine these temperature fluctuations and that has characterized them in order to seek out their explanation. The data used in the research program I'll describe obtained in these two telescopes. The one on the right, the Hubble Space Telescope, a similar aperture telescope in Baja California, San Pedro Marte Observatory, was used for the ground-based observations. So this is a program that intensively used observations here in Mexico for high resolution, velocity resolution spectra, and also for low resolution, photometrically calibrated spectra. The target object in our study is this, the Ring Nebula. And this image is an early Hubble image of it, about 14 years old at this point. That image was made with the Wide Field Planetary Camera 2. That's the camera that was installed in the first servicing mission of the Hubble. That Wide Field Planetary Camera, one of the CCDs could image the entire Ring Nebula. That camera was replaced at the most recent and unfortunately last servicing mission by the so-called Wide Field Camera 3. The field of view of that Wide Field Camera 3 is shown here, and the nebula fits into it nicely. But a good thing in the Wide Field Camera 3 is that it included a set of filters that were for specialist nebulae. And for that, we owe an eternal thanks to Bruce Ballack, who was on the committee picking the filters. But those filters image only a small section of the full field of view. So this is a section that we image with the new wide field camera with the usual filters that isolate the usual diagnostic lines for gaseous nebulae that allow us to determine the densities by looking at each line of the sulfur 2 doublet, of looking at the auroral and nebular lines of both nitrogen and oxygen. So it has a very special set of filters. But those filters needed to be calibrated accurately. And we did an internal calibration by making San Pedro Marte slit observations across the Ring Nebula. And then in the region common to both Wide Field Camera 3 and the low resolution spectra, we could calibrate the filters. And from that, we could get flux-calibrated, pixel-by-pixel images of the nebula. This is a result of the recent Wide Field Camera 3 imaging. This is color-coded scientifically, so that the region of the emission helium-2, which requires the most energetic ultraviolet photons for its production, is shown in blue. Oxygen, 3 forbidden lines, which require an intermediate stage of ultraviolet photons for their production, is in green. And red is nitrogen-2, which require the lowest energy UV photons for its production. So it's a scientifically, astrophysically coded, color-coded image. And you see, in addition to the well-known ring structure, the ubiquitous dark knots that you see around. And actually, these condensations are found in all well-studied planetary nebulae. That is, in a program with the Hubble, we found them in all nearby bright planetaries. Now, this is not the optical region is not the entire story. I've combined here that previous optical image with an image made by Dave Thompson with large binocular telescope. The 2.12 micron line of H2. Sorry, you can hardly see it there. So the red in this case is both nitrogen and H2. And there you see how the outer halo, the double halo of the ring, shows up well in molecular hydrogen. Okay, some relevant numbers are here. A decimal needs to be there. You can read those faster than I can. Important thing, the dynamical age is about 4,000 years. Its present star conditions are this. And the ring nebula, like most planetary nebulae, has already passed through the phase when all of the ejected gas has been completely ionized. And then as the star has dropped in luminosity, then the outer parts of the main disk have become neutral again, a recombination period. Now, as the nebula is expanding, continuing to expand, there's this delicate dance of the ionization front between the wanting to get bigger because lower density, get smaller because the ionizing luminosity of the star is dropping. But at this time, Will's calculations are such that we think that the ionization front is actually growing into that neutral material. So it's an important part of the story because of explaining the outer regions. You look at an H-alpha only image of it here. H-alpha is useful, but it doesn't, to the person building a model of the nebula, it's not particularly useful because it comes from the entire ionized region. So it's easiest to understand the object by looking at ratio images. So here, the doubly ionized helium, as compared with H-alpha, you see it's concentrated to the core. The oxygen, doubly ionized oxygen, forbidden line, the oxygen is further out. Nitrogen 2, further out still. Sulfur 2, further out still. And of course, the H2 molecular hydrogen even further. A brief tutorial on photoionization. If the ionizing star is over here, illuminating a sample of gas, the innermost regions will be the highest states of ionization. Opacity is dominated by helium-2. It defines an ionization front for that ion. It's traced best by this line, 4686, angstrom line. The next level of stratification, intermediate level ions, best tracked by this line. The next stage, lower of ionization, including these ions, best tracked by these emission lines. Then the ionization front itself for hydrogen, best tracked by sulfur 2 and oxygen 1. And of course, just beyond that, conditions are tracked by molecular hydrogen. So that we can identify specific emission lines with different levels of photoionization. So in a simple nebula, you would expect to have just a monotonic change of the ratio of lines. Whereas if you trace the profile of different emission lines going across the object with the central star being here, you see what you expect with helium-4, a little hole in the middle of that, obviously, but you see multiple peaks and valleys in the ratio, telling you that somehow we're looking at multiple ionization fronts. We're not looking at a Strombolian sphere viewed edge on. Now, in order to address the t-square problem, you really need a three-dimensional model, and building a three-dimensional model requires having good radial velocities, which we obtain with Mezcal at this resolution from San Pedro Marte, mapping the entire nebula. The characteristic spectra are shown here. And the important thing is that actually we found that there were two systems of velocities, one for that main ring. So these are slit spectra across the object. So the main ring spectra are shown here. And then when you expose them later, you see the spectra of the outer system. What is in 3D an outer system, but looks like it's the middle of the nebula. So that we actually have two velocity systems present in the object. That is, the main ring has a lower characteristic velocities, and you can read the numbers here. So these are the expansion velocities of its shell. And then when you look in the center, near the central star, there are higher velocities. Now, even though you're looking close to the central star, you still see low ionization lines, which means that the object is ionization bounded in this direction too. I don't have time to go into the details of it. The main ring that you see there is, because it's not circular, what we're seeing is not a circle viewed at an angle that makes it an ellipse, but rather it's an elliptical object viewed almost flat on. And there are numerous arguments for that, including the fact that the smaller dimensions are brighter, and with an ionization front, with Ferland's mechanism, as I call it, how bright it is depends on the distance from the central star. And that's why those sides are brighter. The resultant three-dimensional model is shown here. That here, the observer is up here. We're looking almost flat on to the object. You see that it's like a bagel, a sesame seed bagel, where you put the sesame seeds on the outside. Except by magic, you've been able to put the seeds just inside the surface of the nebula. So here, it has numerous knots around on the inside of the nebula. The outside of the bagel is defined by an ionization boundary. There is material in the center, so it's actually more like a jelly donut than a bagel. So there's a low-density material here, and then low-density material rising above and below it. So this is a bipolar nebula. But we can derive a good 3D model because of favorable orientation. Then outside of that are the so-called inner halo, very scalloped, and an outer halo, both of those well seen in molecular hydrogen, that is nearly circular in form. I promised that we would be able to determine densities from the emission line images. So the images of the two lines of the sulfur doublet have allowed us to determine densities in those regions. And if you look along the long axis, the so-called x-axis of the nebula, you see densities, like 500, 400. When you look in the across the short axis, you see comparable densities. What we're seeing here as we get in close to the star are regions obviously in the foreground part of the nebula. But our goal was to study temperatures. So from the auroral to nebular lines, line ratios, after correction for reddening, of course, one could derive electron temperatures just on a slit, a profile across the nebula. And you see for the region where oxygen emission arises, we have a slow decrease in the electron temperature going away from the star. The nitrogen emitting region is farther out from the central star, but in the region of overlap, you see the temperatures are very consistent with one another. And of course, remember, we're looking at a three-dimensional object in 2 dimensions. So that this emission here of the oxygen-3, even though it comes from near the central star on the plane of the sky, must be coming from the foreground. So the oxygen-3 temperatures from close to the central star are not a good guide of the temperature of the gas physically close to the central star. That we found out there was a way to get temperatures in the middle, and Will took the lead on this, in that I had noted there was an anomaly in the continuum brightness of the nebula. That is, the photoionized plasma gives you both emission lines for collisional recombination processes, but also a continuum of emission through recombination and through free collisions. That for a pure hydrogen gas at around 10,000 degrees, the ratio of strength of the continuum to, say, the H-beta recombination line are such that it would take about a 1,800 angstrom sample of the continuum to have as much energy in it as that H-beta line. Now, helium is, doubly ionized helium is a strong emitter of continuum, but we can determine how much continuum there should be if it were a gas at a particular temperature. And you look at this profile of something that's called the equivalent width, which is that sample size in the continuum you have to take to equal the energy in the H-beta line, as a function of position as you go across the nebula. So this is from the Hubble images. These are across the short axis. These are across the long axis. Even these numbers are a problem to interpret unless, as Will points out, the temperature is much higher than in the oxygen-free zones. Well, it's such a dramatic, unexpected result that we also looked at San Pedro Marte low-resolution spectra, see if they gave the same answers, and they do. The same pattern, numbers that are very similar, not identical because they're scattering in the spectrograph, but the same properties. So it's a believable thing, and when you take the liberty of varying the temperature, knowing the ionization conditions, you see that in the central part of the nebula, it gets up to about 13,000. Now, we all know, students of gaseous nebulae, one of the first things you learn is temperatures should be constant throughout the objects. So this tells us that there are processes operating that are not at the level of introductory photoionization theory. Now, this big drop in the equivalent width of the outside is actually caused by the dust that's out there scattering light from the general radiation field. So, if we can determine profiles from the images of the electron temperature, we can always also determine temperatures point by point across that small part of that quadrant of the nebula where we had the best images, that is, the full set of images. The t-squared problem is the thing we wanted to address. You can define, as Manuel and Raphael have defined it very early, the average temperature, the temperature fluctuations, these are weighted by the emissivities. But what you observe is not a probe within the nebula, but rather you're looking at conditions along a column, so that what one can actually hope to derive is an area fluctuation in temperature, and then relate that to a three-dimensional fluctuation in temperature. And of course, to do this, you have to remove the large-scale trends that we saw do occur. And this t-squared in area sample was calculated in various bin sizes. And the results of this part of the investigation done by Will are shown here. Left-hand scale, the oxygen temperature results. Right-hand figure, nitrogen temperature results. These now, the ordinates are the temperature fluctuations per area. The abscissa, both sides, are the bin size of the sample as you go around the different parts of the image where you've derived temperatures. And we're showing here on each the solid line the fluctuations that would be expected from the noise in the instrument. That is, there is a noise from the charge-coupled device because of simply the photon rate and the noise in reading them out. The results have been corrected. The fluctuation results have been corrected for that, but this is only here to show that over most of the range, these corrections are small. So what Will found is that the largest size, the temperature fluctuations slowly increase, and then you get smaller and smaller. that the noise gets higher and higher, the temperature fluctuation, even corrected for noise. So it's the important conclusion that of this is that the temperature fluctuations exist at a sub-arc second scale, well under 1 second of arc, at a microscopic level as compared with the size of the nebula. So that the bottom line numbers is that the t squared for this nebula, 0.05, with this a good uncertainty, whereas the fluctuation you would expect from the theoretical modeling of cloudy is much smaller. So something is going on that we don't understand at the smallest levels of the gas. And this is a common property of all planetary nebulae and gaseous nebulae. There's something we're missing. Now, there may be explanations like turbulence driven by photonization of the knots that we see there, pockets of high metallicity gas, or shadowed regions behind these optically thick knots. I'll close with describing a related thing in our study of the nebula in 3 dimensions, in that we are now able to compare very early Hubble images with recent ones. It's not been possible to do that until recently because the geometric distortions, the optical distortions of the early cameras were not the same as the new cameras. But now, careful studies by the people at Space Telescope Science Institute have determined those corrections, so you're now able, at the level of, I need to say this right, of 8 milliarc seconds or better to align the old and new images, all parts of each image. And that's something, a process called AstroDrizzle. We have images made over almost 13-year interval. We can align them with good accuracy and look at the motions in the plane of the sky over this period. And we can see the results that, let's look first at the nitrogen 2 emission. Remember, it forms right close to the ionization front. And you see the different samples of the all moving radially outward. But then we use the oxygen 3 images to determine the motion of these dark knots that we see in this nebula and many other planetary nebulae. And those results are shown here. That is, these dark knots are expanding outward also. Now, that was a result of taking individual knots and measuring their motion, or individual bright features, measuring their motion. It also determined that what was the magnification. That is, it's long been thought since 1950 when Olin Wilson said it that how explosive expansion was occurring in planetary nebula. It's a more accurate thing to say homologous expansion was occurring. That is, where the faster moving objects are farther away. So it's essentially like the old picture of expansion of the universe, that there would be a Hubble constant that was common to everything, nearby and far objects. velocity divided by distance, a Hubble constant. So in my case, I phrase it as a magnification factor. So we did process a series of images where we took the first epoch image, magnified it in steps, until finally, when you could produce an image that was identical to the new image by magnifying the early image, and that gave you the magnification factor. And I did that with various samples, both for the knots and for the nitrogen region, and with the following result, that there's a regular pattern of expansion, that there's a possible difference in the expansion scaling factor, call it the Hubble constant, if you will, between the major and minor axes. That is, something went on early to cause this thing to be distorted. And there is a probable difference between the Hubble constant for the dark knots and its host molecular gas. And that must tell us something about the formation of those knots. Now, there was mention yesterday of the thesis work of Yolanda on taking the VLA images of planetary nebula, combining a tangential motion with an expansion motion and deriving from that a distance to the nebula. This is, you can do the same thing here, except vastly more accurate than was possible at that time. That gives you what I call a dynamic distance to the nebula. And the magnification factor also gives us the age, the reciprocal, like a Hubble constant age. These are the two publications already out that cover this, that going back to the original theme, which model did we produce? The one on the left or one on the right? And thanks to the hosts, our hosts, for allowing me to talk about this work here this morning about this beautiful object.
I was wondering about the status of searches for a companion to the central star. And the second question, if I get it in quickly. Did you ever attempt to get Spitzer spectra for this object?
The search, of course, it's a loaded question because many people want the binary structure to determine the disk, the non-spherical disks that come off of planetary nebulae. That in only one case, and that's published quite recently, do you actually see spectroscopic variation, where you see optical binary stars. They are so widely separated that they just, even if they're true binaries, they're so wide that they should not have shaped the ejection of the gas. But still, it's a very attractive thing. But it would be great to win the prize that's been offered to prove that there are binaries in planetary net. But this great, personally financed, not by me, prize has yet to be claimed. Now, Spitzer spectra have not been made of the outer region because this is not one of those very high surface brightness planetary nebulae. Now, the helix has been studied with other infrared spacecraft, and we understand the process of emission, in particular of the H2, which is not at all what the people who build spacecraft and take pictures interpret it to be, which is shocks. But it's simply not that, but rather a very subtle mechanism that came up, which allows this to be generated just beyond the ionization fronts. Now, one thing I didn't point out in the talk, a real oversight, is all of this outer radiation, this fossil radiation, results from this earliest stage of photoionization, including that H2 emission.
What is the currently accepted theory or model for the formation of these dark globules, and so-called? I remember a paper by Capriotti 4 years ago.
Yes, about the formation. He argued it was Rayleigh-Taylor instabilities. And there have been multiple instability mechanisms invoked since then. Vishniak, Guillermo from Ensenada, all instability phenomena. To me, those are the most attractive because when you look at the knots, they're all close to the ionization front. They're not down in close. The other school of thought is John Dyson's, that these are condensations that's formed in the stellar atmosphere before expulsion. But I don't think that they should have survived, and certainly Pat Huggins' study with VLA looking for them in very small planetary nebulae couldn't find them. So they are, I think, are almost certainly an instability near the ionization front. And it's very important because as well as we can calculate it, there's as much mass in these knots as in the rest of the nebular shell. So this trapping mechanism is very, very efficient. So it's something one really cannot ignore. And that's why when we're trying to explain the T-squared process, the physics, the mechanism that's driving the T-squared process, and look at very small scale, a lot of those theories are tied to the knots. That is through photoionization, often through shadowing behind it.
Is the T-squared that you derive consistent with what you need to explain the difference between the recombination line and collisionally excited line abundances?
Yes, so they're absolutely consistent in this case, but it's still an empirical, it's a phenomenological thing. What we can explain the abundant discrepancy, but we can't determine the T-squared factor for more distant objects, and therefore come up with a general formula that you can apply to those objects that you can't observe as well.
In determining the equivalent widths of the lines, did you include the two-photon emission process as a source of continuum emission?
It was part of that. Since we know the densities, we could,
Calculate that. Yeah.
We could make the correction for quenching that occurs by collisional deexcitation. So yes, two-photon was considered in it, and where it's really unusual here is because you have an ionization object, and helium-2 is a very efficient emitter of continuum. But fortunately, we know the degree of ionization. Mm-hmm. So I think we used all of the known.
So it was not very important.
It was not
okay,
in this
thank
case.
you.